Okay, hello everyone. Now our topic is distributed load. What is a distributed load? Just think that you have an object, okay, and just consider. Let's see what I have. Two objects. So this steel ruler and the tape. Now I'm pressing on the steel ruler with the tape. As you see that the contact region is flattened, okay, and in fact there exists an area that load is transferred from this tape to this steel ruler. As a result, even if I apply a certain load onto the tape, this load is distributed to the certain region of this steel ruler. Now the point is, I want to calculate the forces that comes to this steel ruler, and certainly I know that it acts on a certain area, and how can I reduce this infinite number of points which is applied to a certain region to a single point. So this is called reduction and reduction of distributed loads. Now, simply let's say that we have a simple beam. It is simply supported at one point, and then there exists a slicer at the other end. And let's assume that our x coordinate is along the beam. Now we have a distributed load, as you see, Wx. In fact, Wx is the magnitude of this distributed load at any point. Now, the point is, I want to determine the equivalent force and the point where it applies. I denote the point with x bar if the length of the beam is L. And the resultant force as Fr. So how can I calculate the Fr? Remember that the magnitude of this infinite number of points has to be equal to the magnitude of my resultant force. As a result, I sum up all the loads which acts from this point to this point. This is what I do. Okay, so basically I do it by integration. As a result, I integrate this Wx, because it's the magnitude, from 0 to L, or along the region where it is applied. This gives me the resultant force. Okay, so this is how I obtained the magnitude of the resultant force. So now the other thing is the location. I mean, how I can determine the location of the resultant force. Now, this is an analogy. In fact, the moment generated by the resultant force has to be equal to moment generated by the distributed loads. Now, if I choose a coordinate system, okay, so I say that it's located, as you remember that I choose a coordinate system along the beam and it is x. In fact, I can take the moment with respect to any point. Certainly, I take the moment with respect to the origin. In fact, the distance between the point load at any location, so here, to the origin is x. In fact, the magnitude is wx, and the moment generated by this force is x multiplied by wx. Therefore, the moment generated by this force is x multiplied by wx. If I sum up all the moments, it has to be equal to the moment generated by the resultant force. As I know Fr, I already calculated the Fr, the resultant force, which is equivalent to the distributed load. I only need to determine the x bar. In fact, then I can easily say that x bar is equal to moment generated by the distributed load divided by equivalent force generated by the resultant force. This basically means that I need to calculate the moment of the area, first moment of the area under the function, and then if I calculate the area of the function and divide one to the other, I can obtain the location of the resultant force. It will be much more clear when we solve the examples.